Welcome to MRS Bulletin Materials News. My name is Markus Bühler, editor of the Impact section publishing new research. So it's my great pleasure today to meet with Professor Amstad of EPFL Lausanne. And Professor Amstad published a really interesting paper in MRS Bulletin Impact recently titled Influence of the Hydrophile-Lipophile Balance of Perfluorinated Surfactants on the Emulsion Stability. And in this paper, the authors discuss really novel ways of creating emulsions using novel chemistry and materials design principles. And so I'm hoping today to ask the authors a little bit about the paper, what they've done, and why they've done it. So good morning, Professor Amstad.
Good morning.
So,
Thanks for having me.
Oh, a pleasure. Yeah, thank you for taking the time. So what I was curious about, if you can tell me first a little bit about what your lab in general does, and then maybe we'll talk a little bit later about the paper, but we'd like to learn a little bit about your research vision, your lab, and your goals.
Yeah. So my lab works on soft materials in general, and a little bit more specifically on polymers. And our main goal is to introduce processes that enable the fabrication of polymers in a sustainable way, but with a good structural and compositional control so that we can introduce different functionalities into it. In that realm, we started working with granular systems because they are well suited for extrusion-based processes, including 3D printing, but not exclusively 3D printing. And the 3D printing we actually stumbled onto because we wanted to vary local compositions for activation purposes. And I was at this point where I realized that there is really not as many methods for polymers that offer good local compositional control. If you look at that for hard materials, actually you find them and you can control the local composition with pretty high precisions. For polymers, it's much more difficult to achieve. Not impossible, but it's much more difficult to achieve. And that is where we started working on the 3D printing. And then I realized that well, you can 3D print polymers, but then you always have to modify the precursors because of the rheological requirements that the process imparts to them. And I was not so fond of introducing real modifiers because if you do that, it makes the recycling and sustainability much more difficult to achieve. That is why we started working on the granular system. Yeah, then we realized that everything becomes very soft because of weak interparticle interactions. There is where we started to actually strengthen them by introducing secondary networks to connect them, which allowed us to get rather stiff materials that are 3D printed. We could vary local compositions, all good, but they were very brittle. And this was the main motivation of actually the paper that we published, because the brittleness came from the fact that we don't have any, or we have very little energy dissipating mechanisms in our system. And so we tried to introduce ionic crosslinks, reversible bonds, and to increase the interparticle friction to actually dissipate energy more efficiently.
Oh, it's fascinating. Thank you. Yeah. So but before going into some of the technical details, which I'm quite curious about, so these emulsions is something you find in, like you wrote in the paper, in a lot of different things, like in food and drugs, cosmetics, agriculture, and paint. So it's pretty universal. And you mentioned the application to making materials and kind of figuring out how to make them stable and robust and tough. But what is the kind of current technology limited by? Is it sustainability? Is it the cost? Where do you come from kind of in improving on these existing methods of creating surfactants to create emulsions? So there must be some limitation in the current way of doing things.
Right. The limitation is mainly cost. So the current surfactants that are used for these systems are extremely expensive. One can synthesize them in the labs, and the chemistry labs synthesize them. There is not a problem. The problem comes from the fact that most of these emulsions with fluorinated surfactants are used by biologists or biochemists. And in many cases, they actually shy away from the synthesis. So they buy them, and then it becomes a cost issue, which means only a few labs can actually afford that. And I was not so happy by this fact. I wanted to make that more broadly available to the community. And then we started to synthesize them and realized that there is a lot of batch-to-batch variations in the synthesis protocols that are published or have been published, because of a lot of different tricks and details that, well, vary if different people do that.
Yep.
And then I had a very good chemistry PhD student that actually took on the lead on that and revisited the synthesis protocol to simplify it, to make it less dangerous, less toxic, and more scalable. And I think that was, that was then the outcome that we published in this paper.
Thank you. Yeah. And so when I want to break down a little bit of what you've explored in there. So the title talks about some balances of hydrophil, lipophil interactions, I guess, and context. And then you have perfluorinated. Can you break us down a little bit? Can you break this down, please, a little bit for a very broad audience who might not have worked in these particular systems before?
Yes. So it is a very particular system where we stabilize aqueous drops in fluorinated oil. And if you want to stabilize that using surfactants, polymeric surfactants, you need to have at least one block that is fluorophilic because you want to dissolve it into fluorinated solvent.
Right.
Just the reason that we chose these fluorinated oils. The reason these fluorinated oils are used a lot by the community is that they're compatible with an elastomer called PDMS, which is used to make these devices from, the microfluidic devices. Okay. Now, there is different types of these fluorinated surfactants, and the main variable in these surfactants is basically the ratio of the hydrophilic block to the hydrophobic block. And that ratio influences the affinity of the surfactant to the interface of the drops. It influences the stability of the drops, which essentially then determines the performance of the emulsions. But because the synthesis of these emulsions was sort of not so robust, it was very difficult to systematically vary, say, ratios of hydrophilic to hydrophobic blocks, because you always have mixtures. You have mixtures between di and tri-block copolymers, mixtures in molecular weights, etc. Often you have some unreacted surfactant that also influences the stability, but is not quantified. And so the result of that is that even if you purchase these surfactants, you have large batch-to-batch variances, and often you have to basically repeat the whole series of experiments because you cannot reproduce them. And so what we try to address here is, with this paper, is to systematically vary the ratio of the hydrophilic to the hydrophobic block of a diblock surfactant, simply because that is the simplest surfactant you can imagine in this realm. And then to give guidelines in terms of design, what ratio you should aim for in the synthesis if you want to stabilize certain types of emulsions, in our case, water and oil emulsions.
Yeah, no, thank you. This is great. Yeah, so it's kind of a very systematic bottom-up fundamental understanding that you've developed here, rather than having the natural variation in basically purchased products. So it gives you a lot more control. And I guess others with this paper can make this themselves fairly reproducibly easily in the lab. So there's sort of a recipe now that you have that can be applied and is very reliable, I guess.
That would be the hope, yes.
Yeah, great. Yeah, that seems to be a big bottleneck in this field, because if you have variation at that level, any experiment you do downstream in your microfluidics or your, I don't know, agriculture, food application, whatever you have, it's going to have a lot of variation as well. So this seems to be pretty fundamental, very important work. So if you want to maybe, talk a little bit about the next steps in this work. So if you maybe could talk about, please, what you yourself and your student, and I think that was the first author, Jaya De Angelis, right?
Yeah.
Pronounced the name correctly, hopefully. And I don't know if the students continue to work on this or you are. So what are you doing, and what are you hoping maybe others can do with this now?
Yeah. So we are currently functionalizing these surfactants to add functionality to the emulsions or particles we made out of these emulsions. Introducing ionically cross-linkable moieties or covalently cross-linkable moieties, or even motifs that respond to external stimuli. And because we can control the surfactant structure now pretty well, we can actually control the surface chemistry then of the resulting particles well. And that is something we're working on. I do hope, of course, that at least the groups that are interested in these research directions follow this trend. My big hope was also with this paper that actually the community that does not really care about microfluidics and emulsions per se, but they care about using these drops to screen or as a method to get high throughput assays, that they can more readily get access to the surfactants needed to actually get these assays to work and thereby boost this technology a little bit.
Great. Yeah, wonderful. Yeah, it seems to be a really important area. And so I want to thank you again, Professor Amstad, for taking the time to speak with us today. And anyone interested in looking at the paper, we're going to put the link in the video and the caption, as well as in the comment section. And so you can find it and take a look at what the team at EPFL has created there. Thank you so much. For more materials news, see mrsbulletin.org and follow us on X @mrsbulletin.